The statement that scientists have located the bottom of a black hole carries the same sensational weight as a headline promising imminent alien contact or the secret to eternal life. It sounds like pure fantasy, wouldn't you agree? For now, let's resist the urge for simple, clear-cut answers, and instead explore this subject not as casual observers of news, but as investigators pursuing the most profound enigma in the cosmos. Is a black hole's bottom a physical reality, or is it an illusion born from our inherent fear of the unknown?
Our story begins in England, in the year 1783, when the Age of Enlightenment was at its peak. Newton had already presented the world with his laws of mechanics, suggesting the universe was a vast, impeccably designed clockwork mechanism. In this world lived John Michell, a man who defied the stereotype of the eccentric scientist. He was a clergyman, the Reverend John Michell, but also a brilliant natural philosopher, geologist, and astronomer, known for his calm temperament and exceptionally sharp intellect. There, in the solitude of his study, surrounded by volumes of books and celestial maps, he posed a question that was both deceptively simple and utterly revolutionary. A question that conceived the first monster of theoretical physics. To grasp his thinking, you need to be familiar with just one concept that anyone who has ever thrown a stone into the air intuitively understands: the principle known as escape velocity.
Imagine you are on Earth, tossing a ball upward. It ascends, then falls back. If you throw it with greater force, it travels higher, but gravity's grasp eventually pulls it down. Now, envision a cannon that can fire a projectile with incredible power. Even if that projectile travels a great distance, the planet's gravitational pull will ultimately win. However, a critical threshold exists, a velocity at which an object can permanently break free of the planet's gravity and start an endless journey into space. For Earth, this speed is approximately 11.2 kilometers per second, an immense but achievable velocity required for our rockets to send probes to other planets. As a man deeply versed in Newtonian mechanics, Michel understood this principle perfectly, and from here, he made a brilliant and almost visionary leap of logic. In his era, the prevailing theory from Isaac Newton was that light consisted of tiny particles called corpuscles. Michel reasoned that if light is made of particles, those particles must have mass, and if they possess mass, then gravity must affect them just as it affects a hurled stone or a cannonball. From this deduction, a monstrous image began to form in his mind. What if a star existed in the universe so massive and dense that its escape velocity was greater than the speed of light itself? Consider a body shining with the intensity of 1,000 suns, yet from whose surface not a single particle of light could escape its powerful gravitational field. Like a thrown stone, light would rise, be slowed by gravity, and inevitably fall back to the star. To a distant observer, this star would be entirely invisible. It would be a colossal, incandescent sphere of matter existing in space, yet its light would be held forever in a gravitational prison. Michel gave these hypothetical objects a chillingly accurate and gothic name: dark stars. This was the very first scientific concept of an object that is invisible by its very nature, not because of distance or dimness, but because it is fundamentally unseeable. A gravitational phantom, a cosmic vampire that exists but emits no light. The idea itself bordered on heretical. Although it was derived from the strict laws of Newton, it described something that felt completely unnatural. This was the first shadow of a future Leviathan, the earliest premonition of an abyss flickering in the human consciousness. Michell even calculated that a star the size of our sun, but with a density 500 times greater, would become such an object. He also outlined how one might detect such a monster. If it had a companion, we would observe the visible star orbiting an empty point in space, an invisible center of mass. A cosmic detective story proposed 2 centuries before it could be investigated. However, Michell's idea, though brilliant, was ultimately a product of its time and incomplete. It was built on the notion of light as tiny projectiles that gravity could physically slow down and stop. His thinking was like a beautiful but fragile sandcastle on a Newtonian foundation. His intuition was correct, but the mechanics were wrong. The true nature of light and gravity would prove to be far stranger and more magnificent than even the most daring mind of the 18th century could have envisioned. As a result, the concept of dark stars was dismissed as a curious novelty and was long forgotten, lying dormant in the archives of the Royal Society like a sleeping prophecy awaiting its hour. For this phantom to become flesh, to transform from a dark star into a black hole, humanity first needed to completely overturn its understanding of reality. We needed to recognize that gravity is not simply a force, that space is not a passive stage, and that light is far more than a stream of fast-moving particles. The specter, born in the imagination of an English clergyman, awaited a new prophet, someone who could explain that gravity doesn't just attract light, but can actually bend the geometry of space and time itself. This new visionary would show that the abyss is not just a place of powerful attraction, but a tear in the fabric of reality. That Gothic tale, told in the language of mechanics, was only a prologue. The main act of the drama was still to come, and it would require a new grammar for the universe, the grammar of curved space and slowed time. And the individual fated to compose this new cosmic grammar was already emerging on the stage of history. He was a young patent office employee who would soon compel the world to question the very nature of time's passage and the certainty of a straight line. The phantom that Reverend John Michell had envisioned, a concept born of Newtonian mechanics, was now awaiting Einstein's mathematics. This ghostly object was a product of an older paradigm, one that saw light as a hail of microscopic projectiles, and gravity as an enigmatic, invisible tether spanning the emptiness of space. Yet, as the 20th century dawned, this traditional machine-like conception of the universe started to show its cracks. A radical shift in thinking was necessary, and it arrived through the work of a single man who redefined our perception of space, time, and gravity itself: Albert Einstein. By 1905, his miracle year, Einstein had already introduced his special theory of relativity, which declared an unbreachable cosmic law. Nothing can travel faster than the speed of light. This universal speed limit presented a significant dilemma, as Newton's law of gravitation suggested gravity's influence was instantaneous. Consider this. If the sun were to vanish abruptly, Newtonian physics predicted that Earth would instantly fly out of its orbit. But how could that be possible if the information of the sun's disappearance couldn't traverse space faster than the 8 minutes it takes for its light to reach us? For Einstein, this wasn't merely a logical flaw. It was a fundamental fracture in the structure of physics. He would spend the following 10 years developing a new theory of gravity that could harmonize with his own groundbreaking insights. What he produced was far more than a simple adjustment to the old model. It was a triumph of human intellect, arguably the single greatest scientific achievement of one person: the general theory of relativity, or GTR, which he unveiled to the world in 1915. At this point, our narrative takes a truly remarkable turn, because Einstein put forth a concept as elegant as it was revolutionary. He argued that gravity is not a force at all, not some unseen hand yanking planets towards a star. Instead, gravity is the consequence of mass and energy warping the very fabric of existence, a continuum he named spacetime. To help you visualize this, picture a massive, tautly stretched sheet representing our flat, empty spacetime. If you place a heavy bowling ball in its center, the sheet will sag and create a deep depression. Now, if you roll a small marble across that sheet, its path won't be straight. It will curve downwards, spiraling into the indentation made by the bowling ball. From the marble's perspective, an external force seems to be pulling it inward, but an outside observer can see there is no force. The marble is merely tracing the most direct route available to it through a curved surface. This is precisely how planets behave. They don't circle the sun because of a gravitational pull. They are following the straightest possible lines through a spacetime that has been warped by the sun's immense mass. In essence, gravity is geometry. Einstein replaced the ambiguous idea of a force with a precise and graceful geometric framework for the cosmos. His equations detailed how matter instructs spacetime on how to curve, and in turn, how curved spacetime directs matter on how to move. The theory was a resounding success. It accurately forecast Mercury's orbit with astonishing precision, a feat Newton's model could never accomplish, and it predicted the bending of starlight around the sun, a phenomenon that was spectacularly confirmed just a few years later. Einstein had orchestrated a symphony that described the elegant cosmic ballet of galaxies and stars. But he had inadvertently unleashed something else. Lurking within the mathematical core of his equations was a profound secret, a monster far more real and menacing than Michel's hypothetical dark star. The irony of this discovery is that the first person to glimpse this monster wasn't Einstein himself in his quiet Berlin office, but another man in a setting utterly hostile to fundamental science. It was 1916, and Europe was consumed by the fires of the First World War. On the Russian front, amidst the thunder of artillery, a 41-year-old German astrophysicist named Karl Schwarzschild found himself. Though he was the director of the Potsdam Astrophysical Observatory, he had patriotically enlisted in the army. During the day, Schwarzschild calculated firing solutions for artillery pieces. But at night, by the flicker of a lamp between bombardments, his intellect sought sanctuary from the surrounding devastation in the purest of all human constructs, mathematics. Having been captivated by Einstein's new theory, he decided, in the very heart of civilization's breakdown, to apply these new equations to the simplest object imaginable, a single, non-rotating, perfectly spherical star. Einstein's equations were notoriously difficult. He himself believed that finding an exact solution was practically unachievable and had settled for approximations. Yet Schwarzschild, a brilliant mind trapped in the crucible of war, accomplished the impossible. Within a matter of weeks, he derived the first exact solution to the equations of general relativity and mailed his findings to a stunned Einstein, who replied, "I did not expect that anyone could formulate an exact solution in such a simple form." Schwarzschild's work perfectly modeled how spacetime curves around a star, but it also revealed a strange anomaly where the mathematics seemed to break down completely. His solution demonstrated that for any given mass, there exists a critical boundary. If you were to compress an object's entire mass into a volume smaller than this critical radius, something truly incomprehensible would occur. At this threshold, the equations indicated that the curvature of spacetime would become infinite. For any outside observer, time at this boundary comes to a complete standstill.
This critical distance became known to history as the Schwarzschild radius, marking the mathematical birth of this cosmic monster. John Michell's theoretical phantom now had a precise location in spacetime, evolving from a mere star that light could not escape into something far more profound, a point where the very fabric of space collapses. This boundary, once crossed, ensures all possible trajectories lead in only one direction, straight to the center. This threshold is what we now refer to as the event horizon, and understanding its nature is crucial. The event horizon is not a tangible surface that you could ever touch or feel. It isn't a physical shell, but rather a demarcation in the geometry of space itself, a definitive point of no return. You can think of it like a river flowing with increasing speed until it plunges over a waterfall. The event horizon represents the line where the current's velocity surpasses that of your fastest boat, making any escape impossible. Even if you were to turn your vessel around and paddle with all your strength against the flow, the current would inevitably carry you toward the falls. The event horizon is precisely that location where space-time itself is rushing inward at a speed greater than the speed of light. Because nothing can exceed the velocity of light. Absolutely nothing. Not a starship, a particle, or even a piece of information can ever get back out. Working in the trenches of war, Karl Schwarzschild described the very edge of this abyss, formulating the equation of destiny for dying stars. He revealed that at the core of Einstein's magnificent theory lay the prediction of an absolute prison, a final point of no return signaling the end of space and time as we understand them. Sadly, Schwarzschild never witnessed the debates his discovery would ignite, as he passed away a few months later from an illness he contracted at the front. His work, however, endured. The equation of fate had been written, and Pandora's box was now open, confronting physicists with a terrifying question. Was this mathematical anomaly just a strange quirk of the equations, something impossible in reality, or could the cosmos truly spawn such monstrosities? Einstein himself was firmly convinced of the former, but the universe, as you will see, proved to be far more inventive and merciless than even he could have predicted. Amid the chaos and death of the First World War, Karl Schwarzschild sketched the mathematical portrait of an absolute void. He demonstrated that Einstein's elegant theory not only governed the graceful dance of planets, but also foretold a point of ultimate, irreversible collapse. While the monster born from these equations appeared mathematically sound, accepting that such a thing could exist in our universe was an entirely different matter, launching one of the most dramatic chapters in the history of science. This chapter shows that scientists are not unemotional automatons working with formulas, but people driven by their own fears, biases, and sense of beauty. The concept born from Schwarzschild's equations was, to many, profoundly ugly. It was an insult to the aesthetic desire for a universe that is harmonious and understandable. The first and most prominent figure to reject this monstrous creation was none other than its own intellectual father, Albert Einstein. As the architect of general relativity, he regarded Schwarzschild's solution with intense revulsion. Einstein conceded its mathematical correctness, but insisted it was a physical absurdity. He was certain that nature must possess some inherent mechanism to prevent such a descent into madness. He argued that in the real world, unlike the idealized realm of mathematics, physical forces like rotation, pressure, and radiation would stop matter from compressing into that horrifying point. For Einstein, the singularity, a point of infinite density and zero volume predicted by the solution, wasn't a forecast of a new object, but a signal that his own theory was breaking down under extreme conditions. He viewed it not as a genuine feature of reality, but as a flaw in his otherwise beautiful equations.
It was as if a composer had written a grand symphony, only for the finale to conclude not with a soaring chord, but with a deafening, painful screech. The composer would insist it was a mistake, a problem with the instruments, not part of the intended music. Therefore, until the end of his life, Einstein refused to accept the physical reality of black holes. The Titan turned his back on his own most frightening prophecy. While Einstein simply disbelieved, the broader scientific community chose to largely ignore the problem, dismissing it as too exotic and detached from reality, a mere theoretical game. Proving that this collapse was not a mathematical oddity, but the unavoidable destiny of massive stars, would require a new hero, one who emerged not from Europe's prestigious universities, but from the other side of the planet. His name was Subramanian Chandrasekhar. In 1930, this 19-year-old prodigy from India, a brilliant physics student, set sail for England to pursue his studies at Cambridge. During the long sea voyage, as he looked out at the boundless ocean, he contemplated the ultimate fate of stars. At that time, astronomers understood that stars were not immortal. They were born, they lived, and they died. Our own sun, for instance, will eventually burn through its hydrogen fuel, swell into a red giant, and finally cast off its outer layers, contracting into a small, dense, and intensely hot object about the size of Earth, a white dwarf. This white dwarf is essentially a stellar remnant where thermonuclear reactions have ceased. So what stops it from collapsing further under the pull of its own immense gravity? The answer was known to be the pressure of degenerate electrons, which is a purely quantum mechanical effect. To understand this, you have to consider one of the foundational laws of quantum mechanics, the Pauli exclusion principle. This principle dictates that no two electrons can occupy the exact same state in the same location simultaneously. When gravitational forces attempt to crush electrons into an incredibly confined space, they push back with tremendous force, a phenomenon you can visualize as a cosmic game of musical chairs. In this scenario, immense pressure builds up not from heat, but from a purely quantum mechanical principle, where electrons refuse to be crowded together. This pressure, generated by what is known as degenerate electron gas, is precisely what halts the continued collapse of a white dwarf, providing the stability it needs to survive. It appeared for a time that this was the very protective mechanism Einstein had sought. A perfect equilibrium where gravity's immense pull is countered by the resistance of quantum mechanics, saving the universe from the paradox of singularities. But while journeying by ship, the young Subramanian Chandrasekhar took the next critical step in this line of reasoning. He decided to combine these quantum concepts with another pillar of modern physics, Einstein's special theory of relativity, which famously dictates that nothing can travel faster than light. Chandrasekhar posed a crucial question. What happens if a star possesses too much mass? The resulting gravitational force would compress it with increasing intensity, compelling the electrons to move faster and faster to fend off the collapse. However, since their speed is capped by the universal speed of light, he concluded that their capacity for resistance must have an absolute upper boundary. Through his calculations, Chandrasekhar identified this threshold precisely. He proved that if the mass of a star's remnant core surpasses a specific value, about 1.4 times the mass of our own sun, the pressure from the degenerate electrons would be completely overwhelmed. At that point, this quantum shield would fail, unable to withstand the relentless crush of gravity. Based on all the physics known at the time, absolutely nothing could stop the star from collapsing further into an inevitable, catastrophic implosion. a discovery that represented the first nail in the coffin for dying massive stars. Chandrasekhar's mathematics demonstrated that for these massive stars, collapse wasn't just a remote possibility. It was their guaranteed destiny, a final fate written into the equations of the universe. He arrived in Cambridge with this revolutionary finding, ready to transform astrophysics. But what awaited him was a dramatic and personal confrontation. His mentor, Sir Arthur Eddington, was the leading authority in British astrophysics and a titan in the scientific community, famous for confirming Einstein's theory of relativity during a 1919 eclipse. Initially, Eddington seemed to support his brilliant young protege. Yet, in 1935, when Chandrasekhar presented his complete findings at a meeting of the Royal Astronomical Society, something shocking occurred. Following the presentation, Eddington took the stage, not to engage in scientific debate, but to publicly humiliate the young researcher. He dismissed Chandrasekhar's conclusion as a reductio ad absurdum, a reduction to absurdity, and openly mocked the very notion that a star could collapse in such a manner. Eddington concluded his speech with a statement that has since become infamous. "I think there should be a law of nature to prevent a star from behaving in this absurd way." You have to consider the weight of those words. This was not a scientific counterargument, but an emotional plea. It was a flat-out refusal to accept a reality that seemed grotesque. For Eddington, much like for Einstein, the concept of a singularity was aesthetically offensive, an outcome too cruel and bizarre for the universe to permit. The sheer weight of Eddington's authority was so immense that Chandrasekhar's groundbreaking work was cast aside by the scientific establishment for many years, forcing him to shift his focus to other areas of research to salvage his career. This episode laid bare the intense drama within science itself. Two of the era's greatest minds, Einstein and Eddington, who understood gravity and stars better than almost anyone, found themselves staring into a theoretical abyss and recoiled in horror, preferring to believe their own equations were flawed rather than accept a cosmos where those equations could break down. Yet, mathematics, unlike people, is immune to fear. The Chandrasekhar limit, as it would later be named in his honor, was undeniable and became a cornerstone for our modern understanding of how stars evolve. It revealed that for the most massive stars, there is no peaceful final stage as a white dwarf. Instead, something far more violent and definitive awaited them. So, rejected by the very pioneers who should have championed it, the idea of inescapable collapse faded into the background, waiting for its moment to re-emerge. The theoretical groundwork for the birth of this cosmic monster had been laid, and even as the titans of physics refused to believe it, stars across the universe were already dying with masses far exceeding the Chandrasekhar limit. Their fate was sealed. Their plunge into oblivion was merely a question of time. The next great challenge for science was to move beyond arguing about whether these phantoms could exist and to begin the hunt for them. A quest to find the Leviathan. Decades passed after Chandrasekhar's discovery and the subsequent rejection of his terrifying prediction by the giants of physics. The concept of collapsing objects, sometimes referred to as frozen stars, was relegated to the fringes of science, treated as little more than a mathematical oddity for theorists to ponder. But the universe wasn't waiting for humanity to catch up. It continued its existence, filled with grand and violent events that would eventually provide the first clues in this cosmic detective story. By the middle of the 20th century, the theoretical picture had sharpened considerably. Scientists like Robert Oppenheimer, the very same man who led the development of the atomic bomb, had already calculated before the war that once the Chandrasekhar limit was surpassed, no known force could arrest the collapse. They even explored the fate of even more massive stars, proposing they might form neutron stars, objects of unimaginable density, where gravity forces electrons and protons to merge, creating a sphere of pure neutrons. But even neutron stars have a mass limit of their own, beyond which the collapse resumes, heading toward the very state Schwarzschild had described. During the 1960s, the work of Roger Penrose and Stephen Hawking made it abundantly clear that a singularity was not merely a consequence of perfect spherical symmetry, as Einstein had once wished. Their proofs demonstrated that the formation of a singularity under general relativity is unavoidable, even when a star spins or collapses in an asymmetrical way. With the theory being so robust, this monster seemed very real on paper, which raised a critical question. How could we possibly locate something in the immense cosmos that is, by definition, invisible? How can you possibly spot pure darkness set against a backdrop of more darkness? The search for a black hole, a term masterfully coined by physicist John Wheeler in 1967, could not be a direct observation. It had to unfold like a cosmic investigation. While we couldn't see the culprit itself, we could search for its victims. We could hunt for evidence of its existence and listen for the cries of the matter it consumes. It was at the dawn of X-ray astronomy that we uncovered our first significant clue. In the early 1960s, the very first rockets equipped with X-ray detectors were sent into space. Our atmosphere, which is a great benefit to us, blocks the vast majority of X-ray radiation from reaching the surface. To view the sky in this spectrum, we had to journey above it. What those initial detectors revealed was simply breathtaking. The cosmos, which appears mostly placid and dark in visible light, was ablaze with brilliant sources in the X-ray spectrum, painting a picture of a sky filled with unseen fires. One particular source, identified in 1964, proved especially captivating. It was situated in the constellation Cygnus and stood out as one of the most luminous X-ray objects ever detected. It was given the straightforward designation Cygnus X1, signifying the first X-ray source in that constellation. But what exactly was this object? What could possibly generate such an incredible amount of high-energy radiation? For a number of years, Cygnus X1 was an enigma. However, in 1971, its precise position was finally determined, revealing a direct overlap with a visible star catalogued as HD 226,868. This was a blue supergiant, a star of immense mass and heat. Yet, a star of this type could not, on its own, produce such a powerful X-ray signal. Something was clearly out of place, prompting meticulous observations. Astronomers began to carefully measure the light from this supergiant and soon detected something peculiar. The star appeared to be swaying. The light it emitted would rhythmically shift, first toward the blue and then to the red end of the spectrum, a phenomenon known as the Doppler effect. This was undeniable proof that the star was not alone. It was orbiting an unseen companion with a rapid period of just 5.6 days. At this point, the scattered fragments of the puzzle began to form a single, unsettling image. A cosmic dance of death was playing out before our eyes. We had a visible, massive, and brilliant giant star performing a swift orbital ballet around an invisible partner. By analyzing the visible star's orbit, including its velocity and period, astronomers could apply Kepler's age-old laws to deduce the mass of its unseen counterpart. The result of this calculation was staggering. The invisible object possessed a mass at least 10 times that of our Sun. Let that number sink in for a moment. 10 solar masses. The Chandrasekhar limit, which defines the maximum mass of a stable white dwarf, is 1.4 solar masses. Even the most generous theoretical models cap the mass of a neutron star at around 3 solar masses. But this object was 10. 10 solar masses, all condensed into a volume so small it was entirely invisible. No known star or stellar remnant could match this description, leaving only one possible suspect: the very phantom that had been haunting physicists for nearly 200 years. A black hole. So, what was the source of the X-ray radiation? It was the death cry of matter being consumed. Picture this celestial pair, the enormous blue star and its invisible, hyperdense companion. The black hole's immense gravity relentlessly siphons matter from the surface of its neighbor. This stream of gas, primarily hydrogen, doesn't fall directly in but is instead caught in a swirling vortex due to its angular momentum, forming a vast, flat structure called an accretion disk. And this is where the true spectacle begins. Within this disk, matter revolves at incredible velocities, approaching the speed of light, causing layers of gas to grind against each other with unimaginable friction. This process heats the material to temperatures of millions, even tens of millions of degrees, a stark contrast to our sun's surface temperature of about 6,000 degrees. Heated to such extremes, the matter radiates intensely, not in the visible spectrum but in the X-ray range. This was the unseen fire that our detectors had registered. This entire process was a perfect example of cosmic detective work. We could see the victim, the blue giant star. We could hear its screams in the form of powerful X-ray emissions from the accretion disk. And while the killer remained hidden, its presence was revealed by the dance of its victim, the star orbiting a void. From that orbital dance, we calculated a mass that left no room for doubt. This was no ghost. This was a Leviathan. The discovery of Cygnus X1 marked a pivotal moment, providing the first compelling, albeit indirect, evidence for the existence of black holes. It elevated them from a theoretical abstraction to a tangible astrophysical object that we could actually observe and study. Of course, the scientific debate continued, with skeptics proposing alternative theories. Stephen Hawking famously placed a bet against fellow physicist Kip Thorne, arguing that Cygnus X1 was not a black hole. A wager he later admitted was a form of insurance. If black holes were proven not to exist, he would at least win the bet. By 1990, the accumulated data was so overwhelming that Hawking publicly conceded his loss. Cygnus X1 was merely the first harbinger of what was to come. In the decades that followed, we identified dozens of similar systems within our own galaxy. We also uncovered supermassive black holes, with masses millions and even billions of times greater than our Sun, lurking at the cores of nearly every large galaxy, including our very own Milky Way. We witnessed stars careening around the core of our Milky Way at astonishing velocities, their movements governed by the gravitational force of an unseen colossus. The search was successful, and we located the lair of this Leviathan. We learned to identify its presence by its effects, but this remained indirect evidence. We were observing the consequences, not the source. We saw the performance, but not the performer. For our bold and inquisitive species, this simply wasn't sufficient. We felt compelled to look this monster directly in the eye and capture its portrait. To achieve this, we embrace the role of cosmic detectives, discovering black holes through the gravitational ripples they imprint on space and the final cries of the matter they consume. Systems like Cygnus X1, along with the supermassive beast at our own galaxy's center, Sagittarius A star, became almost standard entries in astronomical catalogs. We were certain of their existence and had measured their masses, holding a conviction as firm as our belief in atoms, which we have also never directly seen. Yet,
This knowledge failed to quench our species' insatiable thirst for understanding. Knowing something exists is one thing, but we possess a fundamental need to see it. The question was, how could you possibly see an object that is, by its very nature, the embodiment of absolute darkness? How could anyone photograph the void itself? The solution emerged once more from the remarkable predictions of Einstein's general theory of relativity. The theory postulated that while a black hole itself is invisible, it must cast a distinct shadow. If you imagine a black hole not in empty space, but silhouetted against a brilliant backdrop, such as the luminous superheated accretion disk we have discussed, a picture begins to form. Light from this disk radiates in every direction. The light that travels directly to us is what we perceive, while the light moving away remains unseen. But what becomes of the light aimed toward the black hole? A portion of it crosses the event horizon and disappears from the universe forever. However, light that passes exceptionally close to the event horizon is drawn into a region of profoundly warped spacetime. Here, the black hole's gravity functions as a colossal, though wildly distorted, lens, capturing light rays and compelling them to bend around its form. Some of these rays might even orbit the black hole multiple times before finally breaking free and heading in our direction. Consequently, if we could observe a black hole with enough resolving power, we wouldn't see a simple black dot. Instead, we would perceive a dark silhouette, a shadow that is actually larger than the event horizon itself. This shadow would be encircled by a warped and twisted ring of light from the accretion disk, its shape contorted by gravity's pull. This luminous ring is effectively a portrait of spacetime itself being bent, and to witness it would be to see general relativity demonstrated under the most extreme conditions imaginable. The concept was elegant, but the scale of the challenge was immense. To resolve such a shadow, a telescope with almost inconceivable power would be required. From our vantage point on Earth, the shadow cast by the black hole at our galaxy's center, Sagittarius A star, would have an angular size equivalent to that of an orange placed on the surface of the moon. No single optical or radio telescope ever constructed by humanity could even approach that level of clarity, making the undertaking seem utterly impossible. It was then that one of the most brilliant concepts in modern astronomy entered the picture: interferometry. The core idea is straightforward. If you are unable to construct a single gigantic telescope, you can instead link together many smaller ones that are spread far apart and make them function as a unified instrument. By synchronizing them with extraordinary precision, the resolving power or sharpness of this combined system is defined not by the diameter of the individual dishes, but by the greatest distance separating them. This principle gave rise to one of the most ambitious scientific endeavors in human history, the Event Horizon Telescope. This is not a single instrument at one location, but rather a worldwide network of radio telescopes distributed across the globe, from the frozen expanse of Antarctica to the Atacama Desert in Chile, and from the volcanic peaks of Hawaii to the mountains of Spain and Mexico. Dozens of observatories and hundreds of scientists across every continent joined forces for a singular objective: to transform our entire planet into one colossal virtual telescope, a single eye with which to gaze into the heart of the galactic monster. Consider the profound humanistic significance of this endeavor. In a world often fractured by borders, politics, and strife, scientists from diverse nations, cultures, and backgrounds collaborated to observe an object 55 million light-years away. This represented a monumental triumph for technology and for humanity itself.
even before a single result was achieved. The project focused on two primary targets. The first was the familiar Sagittarius A star, the black hole at the center of the Milky Way, which is comparatively close, but whose small shadow is obscured by clouds of gas and dust. The second candidate was located at a much greater distance, but was also vastly larger. The supermassive black hole at the core of the giant elliptical galaxy Messier 87, also known as M87. This galaxy lies 55 million light-years from us, but the beast at its center is a true behemoth, with a mass estimated at 6.5 billion times that of our Sun. It is so colossal that its shadow, despite the immense distance, was predicted to have roughly the same angular size as that of Sagittarius A star. During several nights in April of 2017, every telescope in the network simultaneously fixed its gaze on the heart of the M87 galaxy. They operated as a single, coordinated system, synchronized by atomic clocks so accurate they would deviate by only 1 second over a span of 100 million years. Each observatory gathered staggering volumes of data, not images, but raw radio signals. The data from just one night was so immense, measuring several petabytes, that it was impossible to send over the internet. Instead, it had to be recorded onto hundreds of hard drives and physically flown to processing centers in the United States and Germany, leading to the joke that the fastest data transfer method on Earth was a Boeing 747 filled with hard drives. It was then that the most challenging phase of the work began. Processing the vast quantities of data took a full 2 years, a period during which the information had to be calibrated, merged, and corrected for interference from Earth's atmosphere and its rotation. 2 independent teams undertook this monumental task to prevent any errors or biases from skewing the outcome. The scientists involved had no certainty of what they would ultimately find. They could only hope, placing their faith in their calculations, their advanced telescopes, and the bedrock of Einstein's theories. Then, on April 10, 2019, the result was unveiled at simultaneous press conferences held across the globe, and the world watched with anticipation. What materialized on the screens was a hazy orange, yellow, and indistinct image, yet its form was entirely recognizable. It depicted a luminous ring of light that encircled a perfectly round, dark center. This was the shadow of a black hole, an image that brought a long historical journey to its conclusion. That single image represented the culmination of centuries of inquiry. It was the final destination on a path that began with an 18th century priest's Gothic vision of an invisible monster, continued through equations scribbled in the trenches of the First World War, endured the skepticism of scientific giants, and followed the careful detective work of searching for indirect evidence. We had at last captured its portrait, a picture that is less a simple photograph and more a priceless artifact. It is crucial to understand that we are not seeing the black hole itself, but rather its silhouette cast against the brilliant glow of superheated gas. We are witnessing how light from matter located behind the black hole is warped by its immense gravity, bending around the object to reach us, and forming the brighter, lower portion of the ring. This image provides direct, undeniable visual proof of Einstein's correctness, as the shadow's size and shape perfectly match the predictions of general relativity, marking an incredible moment of triumph. Consider the scale of this achievement. Humanity, a small species on a minor planet, managed to synchronize telescopes across the globe, effectively turning our world into one colossal lens to photograph the edge of reality, some 55 million light-years away. We have gazed into the eye of a galactic behemoth, and now, armed with this definitive portrait, we are poised to embark on the next phase, a journey so dangerous it can only be undertaken in the realm of imagination, the fall into the abyss. Now that we have the portrait of the shadow and have confirmed that these monsters are real, we find ourselves standing at the precipice, staring into the void. Human imagination, however, is not content to simply observe from a safe distance. Its nature is to leap. And so, we commence the most peculiar, solitary, and irreversible voyage in the cosmos. A thought experiment of plunging into a black hole. A trip with a one-way ticket to eternity from which there is no return. Let's imagine you are an intrepid astronaut whose ship has suffered a complete engine failure, leaving you on an unavoidable trajectory toward the event horizon of a black hole. We will stipulate that it's a supermassive black hole, akin to the one at the heart of the M87 galaxy, possessing the mass of billions of suns. This detail is crucial, for reasons that will soon become apparent. Your colleague remains aboard the main ship at a secure distance, observing your descent through a powerful telescope. At this juncture, reality itself fractures into two entirely different narratives, both of which are considered completely true within the framework of general relativity. Let's begin with the viewpoint of your friend, the external observer. They watch your ship get closer to the invisible boundary of the event horizon, and as you do, a strange thing begins to happen. From their perspective, all activity on your ship starts to slow down. So if you were to wave, the motion would look sluggish and drawn out. If you were to switch on a blue light, your friend would see it gradually shift to green, then yellow, and finally red in a phenomenon known as gravitational redshift. The black hole's intense gravity literally stretches the wavelengths of light, decreasing their energy. To your friend, your time is decelerating, an effect that grows more pronounced as you approach the horizon. Your movements become painfully slow, and your image appears progressively dimmer and redder. Then, at the very instant your own clocks would show you crossing the event horizon, the most peculiar thing happens from your friend's perspective. You freeze. Your image appears suspended at the very edge, becoming infinitely faint and red until it fades from sight completely. According to your friend, you never cross the event horizon at all. You simply become a permanent fixture on its frozen surface, your entire infinite future inside collapsing into a single moment on its boundary. But what is your experience? For you, the story is completely different. Time continues to flow normally. The watch on your wrist ticks at its usual pace, and your heart beats with a familiar rhythm. You feel no slowdown whatsoever. Looking out at the universe, however, you witness the opposite. Cosmic events begin to accelerate at a fantastic rate. Stars streak past and galaxies warp as you watch the entire future of the universe unfold in what seems like a few brief moments. As you finally reach the event horizon, you discover it is not a wall or a tangible surface. There is no brilliant flash of light, no physical barrier. You pass over this conceptual line without even realizing it, much like crossing the equator on our planet. The location itself is unremarkable, but in crossing it, the fundamental rules have changed. You are now inside, having completed the most isolated journey in the cosmos, and you are forever disconnected from the universe you left behind. No message, no signal, no plea for help can ever escape. And it is at this point that we can appreciate the choice of a supermassive black hole. If you were falling into a much smaller, stellar mass black hole like Cygnus X1, your story would have ended before you even reached the horizon, because you would have been torn apart by tidal forces. To understand this, imagine you are falling in feet first. Your feet are slightly closer to the black hole's center than your head, so the gravitational force they experience is exponentially stronger. This vast difference in gravitational pull would begin to stretch you apart. At the beginning, you would notice a subtle tug, which would then grow in intensity, elongating your form until your body is ultimately pulled apart into a slender filament of atoms. Physicists have a darkly humorous name for this phenomenon: spaghettification. However, in supermassive black holes, the event horizon is situated a great distance from the central singularity. While the gravitational field there is immense, it is also incredibly uniform, meaning the difference in pull between your head and your feet would be almost non-existent. As a result, you could pass through the event horizon of a supermassive black hole completely intact, remaining alive and conscious to face your destiny moments later. Once you are inside, what comes next? Where can you go? This is where the true terror of the situation reveals itself, because you are left with no choice. Within the event horizon, space-time becomes so profoundly warped that every conceivable path in all spatial directions converge on a single destination: the center, the singularity. Picture space itself transforming into a one-way conveyor belt, carrying everything inexorably toward a shredder. You could attempt to fire your engines, to maneuver sideways, or even to fly backward, but it would be as futile as trying to swim upstream against the flow of time itself. The downward vector toward the center ceases to be a mere direction in space and instead becomes your future. Your rendezvous with the singularity is just as certain as the arrival of tomorrow is for us on Earth. As your descent continues, the tidal forces will mount relentlessly. Even within a supermassive black hole, a point will arrive when you feel the stretching begin. Your vessel will start to warp and then be torn to pieces, and your own body will suffer the exact same fate. In the end, what is left of you, a stream of elementary particles, will plunge toward that final point, where space-time's curvature becomes infinite, and reality as we understand it ceases to exist. This is a journey with no return. It's a voyage where time and space exchange their roles, where your future is no longer an instant in time, but a specific location in space. This is the ultimate solitary flight, as no one will ever learn of what you witnessed or experienced. Your fall is a descent into absolute oblivion. Now, alongside our hypothetical astronaut, we arrive at the central mystery we started with. We are falling, but to where? What exactly is this bottom we are hurtling toward? What is the singularity? Is it the point where general relativity, our most successful theory of gravity, concedes defeat and offers no more answers? As our imaginary astronaut, long since disintegrated into a flow of elementary particles, rushes toward the inevitable, we are approaching an answer. We have mentally crossed the point of no return. Imagine the schism in reality between an external and internal observer, and grasp that inside a black hole, every path leads to one destination. But what is that destination? We pose the question, where is the bottom of a black hole? And after this extensive journey, we can examine the solution provided by classical physics, the solution of Einstein and Schwarzschild. The bottom is a moment in time. Let me restate that for clarity. The bottom is not a place, but a moment. The base of a black hole is not a solid surface you could collide with, nor is it the rocky floor of some cosmic abyss or an object of ultra-high density with physical dimensions. In the context of general relativity, the bottom of a black hole is an event in time, the endpoint of every possible trajectory. This event is what we call a gravitational singularity. In the simplest model of a non-rotating Schwarzschild black hole, the singularity is a point of zero volume and infinite density, where all the mass of the original star and everything else it has consumed is compressed into a dimensionless geometric point. In the more plausible scenario of a rotating Kerr black hole, the singularity takes the form of a ring with a specific radius and zero thickness, spinning at incredible speeds. Yet, whether it is a point or a ring, the fundamental concept remains the same. The singularity is the boundary where our current understanding of physics breaks down. It is the location where the curvature of spacetime becomes infinite. This infinite curvature means the tidal forces that stretched our astronaut also become infinite, capable of stretching and compressing any object into nothingness. This is more than mere destruction. It represents the total annihilation of the structure of matter. This is the bottom in the classical interpretation, the absolute end of the line. It is not just the end for our astronaut, but the end of space-time as we comprehend it. At this juncture, concepts like here, there, before, and after become entirely meaningless. The laws of physics that elegantly describe everything from a falling apple to the universe's expansion simply fail to operate, producing nonsensical results like infinities and division by zero. This is a blank spot on our map of reality, a place where dragons might lie. It is the bottom of existence itself, marking the limit of our language, our imagination, and our most triumphant theory of gravity. Here, it is vital to be completely honest. When a scientific theory yields a prediction of infinity, it almost never suggests that something truly infinite exists in nature. Instead, it signals that the theory has reached the limits of its own applicability. The singularity is essentially general relativity's admission that it cannot describe what happens at this extreme. Einstein's theory is a brilliant framework for the macro world of stars and galaxies, but it has no knowledge of the quantum mechanics that governs the micro world of particles. The singularity is precisely where these two domains collide, as a macroscopic star is crushed down to quantum scales, demanding a new theory that can unite the two great pillars of 20th century physics. At this juncture, the two concepts are locked in a fatal conflict. Our understanding of physics currently lacks a unified theory of everything, specifically a theory of quantum gravity, that could articulate what happens during such an encounter. We are without the vocabulary to describe events at these inconceivable densities and energy levels. Consequently, the singularity is less a tangible object and more a confession of our present scientific ignorance. It serves as a placeholder, a blank space on our cosmic map that will only be filled in once we develop a new, more complete theoretical framework. Yet, what if we engage in a bit of informed speculation, all while operating within the established rules of classical general relativity? Roger Penrose, a key figure in shaping our modern view of black holes, proposed a hypothesis he named the cosmic censorship principle. In essence, he suggested that nature acts as a sort of cosmic censor, tastefully concealing its most extreme creations, the singularities, from our observation. It achieves this by invariably shrouding them within an event horizon, meaning we can never witness a so-called naked singularity. The event horizon functions as a shield, insulating the wider universe from the chaotic breakdown of predictability that occurs at a black hole's core. While the laws of physics may disintegrate on the inside, order is maintained everywhere else in our cosmos. So, you might ask if this is the end of the story. For decades, it certainly seemed that we had found the ultimate bottom, a point of pure ignorance and non-existence, securely veiled by the horizon. A black hole was considered the final prison from which nothing that entered could ever return. It only consumed, never yielding anything back. But then, a man whose name is now inseparable from the study of black holes entered the scientific stage. This individual, though confined to a wheelchair, ventured further in his mind than any spacecraft has ever traveled, and he was about to make a discovery that would overturn everything. He perceived a faint whisper coming from the abyss itself, a message that revealed black holes are neither entirely black, nor are they eternal. Stephen Hawking was on the verge of proving that this abyss doesn't just swallow matter and energy. It also slowly radiates it away. Before the mid-1970s, the accepted model of a black hole was complete, albeit terrifying. It represented the final stage of collapse, a one-way path in the universe with absolutely no possibility of return. Anything that crossed the event horizon, be it light, matter, or information, was gone for good, contributing only to the black hole's mass and causing it to grow. This principle was known as the no-hair theorem, which stated that a black hole is definable by just three external properties: its mass, its electric charge, and its angular momentum, erasing all other complex details about its origin. It was against this seemingly settled picture that Stephen Hawking made his revolutionary contribution in 1974. While investigating the behavior of quantum fields near an event horizon, he sought to unite the principles of quantum mechanics with the warped spacetime of a black hole, a challenge at the absolute frontier of theoretical physics. In doing so, he uncovered something so unexpected that he himself found it hard to accept at first. Black holes are not perfectly black. They must emit a faint glow, a form of thermal energy now known as Hawking radiation. How could this be possible? How can anything manage to escape from beyond the event horizon, a boundary famously defined as the point of no return? The explanation, as is often true in contemporary physics, is found within the bizarre and counterintuitive principles of quantum mechanics. According to quantum field theory, what we perceive as a vacuum is not empty at all. Instead, it is a roiling cauldron of energy from which pairs of virtual particles and their corresponding antiparticles constantly spring into existence, before almost instantly annihilating each other. So, what occurs if one of these fleeting pairs comes into being at the very precipice of an event horizon? Picture it. An electron and its antiparticle, a positron, emerge from the vacuum right at the edge. One of three things can happen. Should both particles fall in or both escape, the event is unremarkable. However, a third, far more fascinating possibility exists, where one particle, the positron, appears just inside the horizon and is immediately pulled in, while its partner, the electron, appears just outside. Now unable to annihilate with its counterpart, this lone electron is flung out into space, creating the appearance that the black hole has just radiated a particle. This emission, however, contains a crucial detail that elevates it from a mere curiosity to a fundamental process. For this newly real, escaping particle to exist, its energy must originate from somewhere, as the law of energy conservation is inviolable. Hawking's genius was realizing that the black hole itself provides the energy. The particle that fell inside, the positron in our example, carries negative energy relative to an outside observer. When it is absorbed, it effectively lowers the black hole's total energy. And since energy and mass are equivalent according to Einstein's famous equation, E equals mc squared, this means the black hole loses mass. Consider the staggering implication of this discovery. Each time a black hole emits a particle through this process, it sheds an infinitesimal fraction of its mass, becoming progressively lighter and smaller. This revealed that black holes are not eternal fixtures of the cosmos. They evaporate, an incredibly slow process, but an inevitable one. The realization that these cosmic giants could eventually disappear was nothing short of revolutionary. This discovery elegantly merged the three great pillars of physics: general relativity, which governs the black hole's immense gravity; quantum mechanics, which explains the spontaneous creation of virtual particles near its edge; and thermodynamics, which assigns a temperature to this resulting radiation. It revealed that a black hole's temperature is inversely related to its mass, meaning the larger the black hole, the colder it is, and the more slowly it dissipates. A black hole with the mass of a star, for instance, has a temperature barely above absolute zero. Its radiation is so faint that it actually absorbs significantly more energy from the cosmic microwave background, the residual heat of the Big Bang, than it emits. Consequently, it will continue to grow rather than shrink. However, in the unimaginably remote future, after the universe itself has cooled to near absolute zero, even these colossal objects will begin to shed mass. As this process unfolds, it accelerates dramatically. The smaller and less massive a black hole becomes, the hotter its temperature climbs, causing it to evaporate at an ever-increasing rate. In its final moments, having shrunk to a microscopic scale, it culminates in a cataclysmic burst, an explosion of gamma rays that signifies the conclusion of its extraordinarily long existence. This reveals the ultimate paradox. The most destructive entities in the cosmos are fated to slowly destroy themselves. The cosmic behemoths that consume stars and galaxies are ultimately subject to a slow, inevitable decay, a concept that feels like poetry expressed through the language of mathematics. Yet, this beautiful and startling finding introduced an even more profound and intricate puzzle. This problem is famously known as the black hole information paradox, and it continues to challenge theoretical physicists even today. The heart of the issue lies in one of quantum mechanics' most fundamental laws. Information within the universe can never be permanently lost. You could, for example, burn a book to ash, but in theory, by gathering every particle of soot, smoke, heat, and light, you could reconstruct every single word it contained. Information simply transforms. It never truly vanishes. Now, let's consider the black hole again. Imagine a book falls past its event horizon. The information detailing every word and letter is now locked away from the outside universe. According to the no-hair theorem, a black hole only retains three properties: its mass, its charge, and its spin. All other details about the book appear to be completely erased. Before Hawking's discovery, one might have argued this wasn't a problem, as the information was simply trapped inside. But we now understand that black holes evaporate. The Hawking radiation they emit, at least in its simplest theoretical form, is entirely random and thermal. It contains no specific information about the objects that fell in, depending only on the black hole's mass, charge, and spin. This is where the paradox becomes unavoidable. When the black hole eventually dissipates into a stream of random thermal particles, what happens to the information about the book? It cannot be left behind, as the black hole no longer exists. Yet it cannot have escaped with the random radiation. This suggests that the information has been utterly and irretrievably destroyed, a conclusion that was nothing short of a scientific catastrophe. It implied a fundamental flaw in either general relativity or quantum mechanics, our two most successful theories of the universe. A true battle of titans was taking place at the event horizon. The question of where the information goes became the modern holy grail for theoretical physics, signaling that our grasp of gravity and quantum mechanics remains profoundly incomplete. It was this very paradox, this whisper from the abyss, that compelled scientists to fundamentally reconsider what lies at the core of a black hole. If the singularity is simply a point of total annihilation, and Hawking radiation carries no information away, then we are confronting a direct violation of nature's laws. Or, just maybe, there is no singularity there at all. Perhaps at the bottom of this cosmic pit, something entirely different exists, something that can preserve information and possibly, one day, release it. The quest to resolve this mystery has spurred the development of some of the most audacious and exotic concepts at the forefront of modern science. We are thus at a critical juncture. On one side, general relativity insists on a singularity, a point of infinite density where information is mercilessly crushed out of existence. On the other, quantum mechanics, through the paradox of Hawking radiation, insists that information can never be lost. This is a direct and fundamental contradiction. This conflict is a clear sign that we require a new physics, a new framework for reality that accommodates neither infinities nor the loss of information. It is here, at the very edge of our understanding, that a great battle of ideas is being waged. Theoretical physicists, much like ancient cartographers facing an unknown world, are attempting to map the blank space where the singularity was thought to be, proposing what might lie at the bottom instead. What if the collapse of matter doesn't proceed infinitely? What if, upon reaching some fundamental quantum limit, it halts, and in place of a terrifying singularity, an entirely new structure is formed, one capable of safeguarding information? Let's explore a few of the most compelling hypotheses, remembering that these are speculative, unproven concepts, yet they are grounded in mathematics and offer potential pathways forward in this search. The first concept, renowned for its elegance, is the Planck star. This idea emerges from theories of quantum gravity, most notably loop quantum gravity, which proposes that spacetime itself is not smooth, but is composed of discrete, indivisible units or atoms. There exists a minimum possible scale, below which physical reality cannot be divided further. This scale is the Planck length, a distance of roughly 10 to the minus 35th power meters. What would this mean for a collapsing star or any matter falling into a black hole? It implies that matter can never be crushed into a point of zero volume and infinite density. Once the compressing material reaches the so-called Planck density, a value of truly incomprehensible magnitude, entirely new repulsive forces predicted by quantum gravity would take over. The compression would stop, having reached the maximum density permitted by the laws of physics. At that point, the matter would bounce back in what is known as a quantum rebound. In place of a total collapse, an explosive expansion occurs, though this entire event is contained within the event horizon. This gives rise to the idea of a Planck star, a hypothetical and exceptionally compact object, only marginally larger than the Planck length, that is proposed to exist at the center of a black hole instead of a singularity. This state is not permanent. Collapsing matter forms a Planck star, which then, over an incredibly long period due to extreme time dilation, explodes and releases its stored matter and information back into the universe. From your vantage point as an outside observer, this entire process would seem to last for an enormous duration, on par with the time it takes for a black hole to evaporate via Hawking radiation. A black hole, then, is not an eternal prison, but rather a portal to a very distant future, where everything that fell inside eventually reemerges. In this model, information is never lost. It's just held in this exotic object for an exceptionally long time. A second, even more exotic and mind-altering idea originates from string theory, one of the foremost candidates for a theory of everything. In this framework, the fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional, vibrating strings. The various vibrations of the same string present themselves as different particles, such as electrons, photons, and quarks. So, what would a black hole look like from the perspective of string theory? In 1996, physicists Andrew Strominger and Qumran Vafa achieved a breakthrough by demonstrating that a black hole could be constructed using the basic elements of string theory. Strings and multidimensional membranes known as D-branes. When they calculated the number of ways such a system could be assembled, they managed to reproduce, with astonishing accuracy, the Bekenstein-Hawking formula for a black hole's entropy, which is a measure of its disorder or information content. This success led to the emergence of a concept called a fuzzball. According to this hypothesis, a black hole is not an empty void surrounding a singularity, but is instead a gigantic, tangled sphere of strings, branes, and quantum energy. It doesn't possess a sharply defined event horizon in the classical sense. Rather, it has a fuzzy surface that exists where the horizon would otherwise be. When something falls onto a fuzzball, it doesn't vanish into a singularity. Instead, it becomes an integral part of this complex structure, with its information woven into the vibrations of the strings, much like adding a new thread to a vast cosmic tapestry. In this view, there is no singularity, no event horizon, and therefore no information paradox. Information is conserved, stored on the surface of this fuzzy ball, and Hawking radiation is the result of intricate interactions on this surface, not a random creation of particles from a vacuum. A fuzzball is essentially an ordinary, albeit highly exotic, quantum object that follows the laws of information conservation, just one that is exceptionally good at masquerading as an Einsteinian black hole. The third idea, which is perhaps the most radical, is connected to the holographic principle. First proposed by Gerard 't Hooft and Leonard Susskind, this principle asserts that all the information contained within a volume of space, for example, the interior of a black hole, can be fully described on the boundary of that volume, which would be the event horizon. This is analogous to how a two-dimensional hologram can store all the information required to project a three-dimensional object. If this holds true, then when a book falls into a black hole, its information is not lost to the singularity, but is instead encoded onto the event horizon, like a holographic script. As the black hole evaporates, this slow process effectively reads the code, carrying the information away with the Hawking radiation, meaning the radiation is not random, but subtly encoded. The challenge is that these correlations are so incredibly weak and entangled that we do not yet have any idea how to decode them. Planck stars, fuzzballs, holographic horizons. These concepts sound like they belong in science fiction, and in a way they do. This is a form of science fiction written in the language of our most advanced mathematics, born from the imaginations of physicists striving to look beyond the veil of mystery. Each of these ideas offers a substitute for the bottomless pit. Instead of a point of non-existence, you have a bouncing star. Instead of a void, a fuzzy ball of strings. Instead of an abyss, a holographic screen. All these hypotheses share a common purpose. They eliminate the singularity. They replace a troubling infinity with a complex but finite physical structure that is, at least in theory, understandable. They rescue information from destruction and represent attempts to reconcile Einstein's vision with quantum mechanics. Which of these ideas, if any, is correct? Perhaps the true answer is something entirely different, a concept we cannot yet begin to imagine. We do not know. To discover the truth, we need a functional theory of quantum gravity, and more importantly, a means of testing its predictions. It's possible that one day you and I will be able to observe the subtle effects of quantum gravity and the gravitational waves from merging black holes, or within the most minute details of the shadow captured by the Event Horizon Telescope. But for now, we find ourselves at this juncture, having journeyed from a ghost in a priest's imagination to the actual portrait of a shadow. We have made a mental descent into the abyss and confronted its greatest paradox. And now we can see a whole landscape of new, astounding ideas emerging where the old, terrifying void once was.
This leads us to the final question. What is a black hole? Is it an eternal mystery, or is it the key to the next chapter of physics? We began our journey with a simple and, as it now seems, almost naive question. Does a black hole have a bottom? We have since traveled across a century, from the gothic premonition of an invisible monster to its precise mathematical depiction, drawn up in the trenches of war. We have seen how the greatest minds of our time shrank from this idea, unable to accept its ugly beauty. We have even participated in a cosmic detective hunt, learning to track this leviathan by observing the dance of its victims. In a culminating triumph of human ingenuity, we combine the power of our entire planet into one great observatory to finally capture its likeness, a silhouette cast against the backdrop of eternity. I guided you on a theoretical plunge into this chasm, where we considered the warping of time and the terrifying process of spaghettification, ultimately arriving at the conventional conclusion: a bottom. This supposed endpoint is a singularity, a location where the fabric of reality shreds and the physical laws we know simply break down. Yet, no sooner had we accepted this concept than a subtle voice emerged from the emptiness, the voice of Stephen Hawking, suggesting the abyss is not permanent because it slowly radiates away. This process of evaporation created the most profound paradox in modern physics, challenging the bedrock principle that information can never be destroyed. So, the question remains, is there a bottom to a black hole? The answer I can offer you now is as intricate and layered as the enigma it seeks to solve. You will not find a classical bottom in the sense of a solid floor you could impact. What general relativity presents instead is a singularity. However, this singularity probably is not a tangible object. It is more like a phantom, a conceptual ghost that arises from the gaps in our current understanding. This is the point where the beautiful mathematics of Einstein's theories become mute, failing to articulate the convergence of gravity and the quantum realm. The genuine bottom, if one even exists in a way you would recognize, is concealed by the shroud of quantum gravity, which remains the ultimate prize for modern physics. The concepts we have explored, such as Planck stars, fuzzballs, and holographic screens, represent our initial, tentative efforts to look past this barrier. They hint that at the base of this void lies not a point of annihilation, but an exquisitely complex architecture operating under new principles we have yet to uncover, signaling not the demise of physics, but its exhilarating next chapter. This reveals the most important lesson a black hole can teach us. All through scientific history, we have faced phenomena that appeared to be insurmountable barriers, the absolute edge of what we could know. Yet every single time, these supposed endings have proven to be doorways. Newtonian mechanics was thought to be flawless, until oddities in Mercury's orbit and the nature of light paved the way for Einstein's universe of relativity. Likewise, classical physics felt complete before the puzzle of blackbody radiation unlocked the bizarre and fascinating domain of quantum mechanics. In our time, the black hole serves as just such a gateway. It is not a final stop or a rupture in existence that you should passively accept with fear. Instead, it represents the most potent theoretical instrument available to us. It functions as a laboratory forged by nature, where gravity and quantum mechanics clash with an intensity that causes the very fabric of our current reality to unravel. By examining these fissures and paradoxes,
We are searching for the route to the next revolutionary theory. A black hole is not a gateway to another universe, as science fiction loves to imagine. We currently have no reason to think so. It is a portal to something far more significant, the next chapter in our comprehension of the cosmos. The fall into this chasm continues, guided not by fearless astronauts in spacecraft, but by our collective imagination and mathematics. The true travelers making this descent are the scientists before their blackboards and computer screens, navigating the abyss with equations and petabytes of data. The narrative of the black hole is ultimately a testament to the human intellect confronting an apparent boundary and refusing to back down. It demonstrates how one idea, sprouting from a straightforward question about light speed, can evolve into a concept that fundamentally questions our perceptions of space, time, matter, and even information. We started by asking what lies at the bottom, only to realize that we may have been asking the wrong thing. A better question might be, what can we learn from the journey downward? The answer to that question is astonishing. It suggests that, on its most basic scales, the universe could be constructed in a manner entirely alien to our everyday intuition. We are learning that space and time might not be primary components of reality, but rather emergent qualities of a more profound foundation. It is possible that reality is holographic, and that information itself is eternal. The intellectual flame first lit by Michell, Einstein, and Schwarzschild has certainly not been extinguished. In fact, it now burns with greater intensity than ever before. This light guides a new generation of physicists as they work to decode that whisper from the void and chart the unknown territory beyond the event horizon. So when you next gaze up at the night sky, think of these unseen behemoths concealed in the blackness. See them not with apprehension, but with profound reverence. They are not merely cosmic tombs, but pledges of new breakthroughs, future revolutions, and even more profound enigmas. Consider them cosmic riddles presented by the universe, as our greatest adventure is to pursue their solutions, to continue our unending and exhilarating descent into the depths of knowledge. Where human inquisitiveness meets technological prowess, the James Webb Space Telescope has made a breakthrough that pulls back the curtain on our universe's distant past. This particular story started when the observatory aimed its advanced near-infrared instruments, specifically NIRCam and NIRSPEC, toward a segment of deep space identified as GOODSS. In that region, an unassuming red point caught the telescope's attention, which further analysis revealed to be a galaxy with a redshift of Z equals 13. What this signifies is that the light from this distant object started its voyage toward us roughly 13.8 billion years ago. The galaxy itself came into being only 330 million years after the Big Bang, at a time when the cosmos was just starting to assemble its first major structures. During that epoch, space was almost completely permeated by a thick fog of neutral hydrogen. According to established theories, this fog ought to have absorbed any ultraviolet light, rendering sources like this one undetectable. And yet, from the object designated JADESGSZ130, which I will simply call J from now on, an entirely unforeseen signal was captured. This signal manifested as a brilliant spectral emission line, famously known as the Lyman alpha. A specific spectral line, which emerges when electrons in hydrogen atoms drop to their lowest energy state, acts as a clear signal that a bubble of ionized gas is expanding around a galaxy. This bubble was likely created by an intense stream of ultraviolet radiation from either supermassive first-generation stars or an active galactic nucleus housing an early supermassive black hole. The very presence of this bubble is what enables ultraviolet light, which neutral hydrogen would normally absorb, to travel unimpeded and ultimately be detected by our instruments. The galaxy known as J exhibits several remarkable characteristics. With a diameter of only about 230 light-years, it is exceptionally compact when compared to the colossal galaxies of today. Yet, its luminosity and the intensity of its radiation are truly staggering. Despite its small stature, this galaxy emits light with a brilliance equal to that of tens of billions of contemporary stars, which suggests that its core harbors either extraordinarily massive, hot stars or an active nucleus furiously consuming matter and unleashing immense energy. There are a couple of prominent theories that attempt to account for such a brilliant light source so early in the universe's history. One hypothesis posits that the galaxy hosted a large number of population 3 stars, which theoretical models suggest were vastly more massive and hotter than any stars born today. These primordial stars could have emitted ultraviolet radiation so powerfully that they carved out huge ionized zones around them, allowing Lyman alpha light to pass freely through space. An alternative explanation points to an active galactic nucleus, where a supermassive black hole accretes nearby material and radiates colossal amounts of energy, which could have also inflated such a bubble. So, why have you not heard about a discovery like this before? The explanation is rooted in a major technological breakthrough. Prior to the James Webb Space Telescope, our capacity to peer into the early universe was severely constrained. Telescopes from previous generations, including Hubble, were limited in their resolution and sensitivity, particularly in the infrared spectrum, which is essential for observing objects with such extreme redshifts. Furthermore, the ancient universe was shrouded in a thick fog of neutral hydrogen that effectively blocked ultraviolet radiation, concealing the dynamic processes occurring within. This research also paves the way for finding other objects of a similar nature. If this galaxy proves to be a typical example of its era, rather than a unique outlier, it suggests the early universe was filled with many such powerful beacons, each playing a role in clearing the cosmic fog of neutral hydrogen. This would give us a much clearer picture of the distribution and properties of the first stars and galaxies, helping you and I understand their profound impact on the cosmic environment. Scientists are already formulating plans for new observations to scrutinize this object and hunt for comparable systems, which will help define the nature of these ionizing sources. Beyond this, spectral analysis has revealed that during the first billion years after the Big Bang, the number of galaxies ceasing star formation was actually 100 times greater than our theories predicted. This discrepancy forces us to seriously reconsider the validity of current models describing the evolution of stars and the cosmos. It seems that science has significantly underestimated how stellar winds and black hole activity influenced the star-forming processes in the universe's first galaxies, potentially halting the birth of new stars much sooner than we thought. And there is more. Within the Webb data, the mission team identified a truly record-breaking discovery, the oldest extinct galaxy ever observed. This object, designated JADES GS-Z7-01-QU, appears to have stopped all activity merely 700 million years after the Big Bang. According to models based on Webb's observations, this galaxy amassed a stellar mass equivalent to over 10 billion suns within its first 600 million years of existence, only to have its star formation shut down abruptly. These findings point to another critical insight. A separate compact galaxy, known as Rubies, measures only about 650 light-years across, but contains a stellar mass density similar to the central hubs of modern galaxies. This has led researchers to propose that the galaxies which went dormant in the early universe may have evolved into the dense cores of massive galaxies in later cosmic epochs, possibly even our own. This possibility provides yet another compelling reason to overhaul our understanding of the universe's true evolutionary path, which we have likely misinterpreted until now. Ultimately, these discoveries remind us that the cosmos is brimming with surprises, and that light traveling for billions of years can still tell incredible stories about our origins. This is a pivotal moment for understanding cosmic evolution, giving us a key to unlock how the universe transitioned from its dark ages into an era of light. It presents you with an opportunity to witness the very first galaxies and stars, and it pushes us to ask how much more we have yet to learn. It is a powerful catalyst for future research that promises to spark revolutionary changes across cosmology and astronomy. The galaxies known as J and rubies now serve as luminous guides, allowing us to peer deep into cosmic history and unlock secrets of the past. Their discovery fuels optimism that we are on the verge of answering profound questions about the universe's creation and the emergence of life. This achievement powerfully illustrates how contemporary science, through collaborative international efforts and state-of-the-art technology, can illuminate the cosmos's oldest enigmas and perhaps reshape our entire perspective on where we came from and our ultimate destiny. A popular sentiment, almost a modern proverb, suggests that the minds behind the legendary Hubble Space Telescope should be honored with statues in every major city worldwide. And this grand idea holds a deep truth. This iconic space observatory's contributions are immense, having revolutionized not just astronomy, but our very understanding of humanity's role in the cosmos. A striking testament to its power is the image it captured of the remarkably remote and dim galaxy designated as UDFJ-395468284. This faint point of light is situated an almost incomprehensible 13.4 billion light-years away from our planet. In effect, Hubble acted as a time machine, giving us a glimpse of stars as they appeared over 13 billion years ago, a mere 380 million years after the Big Bang. During that primordial epoch, the universe itself was just a cosmic infant, starting to form its earliest, delicate structures from the foundational gas. It is almost certain that the celestial objects whose light reaches us now have long since vanished from existence. Billions of years ago, they were likely destroyed in cataclysmic explosions, or consumed by the gravitational pull of more massive galactic neighbors. What we are detecting is merely a phantom-like echo, a message composed of photons from stars and galaxies that died eons ago, a message that has journeyed across expanding spacetime to finally arrive at our telescope's mirror. Despite its incredible achievements and undeniable greatness, the Hubble telescope remains a marvel of last millennium technology, having been placed into orbit back in 1990. In the decades that followed its launch, scientific and technological advancement has surged forward at a revolutionary pace. This progress has introduced novel materials, new data analysis methods, and engineering concepts that were simply beyond the imagination of Hubble's original creators. This wealth of innovation, accumulated knowledge, and cutting-edge engineering has been masterfully integrated into Hubble's much-anticipated successor, the James Webb Space Telescope. So what is it about this new observatory that generates such excitement among both scientists and space enthusiasts? Let's explore the unique instruments it carries and the new frontiers it promises to unveil, to see if this new cosmic sentinel truly lives up to its remarkable reputation. Let's begin by examining the fundamental specifications. The new telescope has a mass of just over 6 tons, which is considerably lighter than its predecessor, Hubble, which weighs 11 tons. The fascinating paradox, however, is that Webb's physical dimensions are vastly larger, despite its lower mass. While Hubble's size is often likened to a school bus, the fully deployed Webb observatory is comparable in scale to a regulation tennis court, stretching an incredible 20 meters in length and standing as tall as a 3-story building. The single largest and arguably most crucial element of the James Webb Space Telescope is its massive 5-layer sun shield. This is not merely a part, but the core foundation upon which the observatory's entire scientific mission rests. The shield is constructed from Kapton, an exceptionally thin polymer film, celebrated for its incredible durability and heat resistance. To enhance its properties, each layer is coated with a near-invisible film of aluminum on the sun-facing side, and a layer of doped silicon on the colder side, protecting the sensitive optics. This sun shield is composed of 5 distinct sheets separated by a vacuum, which serves as a perfect thermal insulator. Such a multi-layered design is essential for shielding the telescope's highly sensitive scientific instruments from the intense heat radiated by the sun, Earth, and Moon. This ingenious engineering solution enables the telescope's detectors to reach an incredibly cold operational temperature of -220 degrees Celsius, a critical requirement for observing the faint light from the most distant objects in the universe. Without this extreme cooling, the telescope's own heat would emit infrared radiation that would overwhelm its delicate sensors, making it impossible to discern the feeble light from the universe's first galaxies. By creating this profoundly cold and stable environment, the shield provides the necessary conditions for achieving unparalleled observational sensitivity. At the core of this intricate observatory is its most captivating feature, the immense gold-coated primary mirror. This is far more than a simple reflective surface. It is a sophisticated optical system designed to gather and concentrate the priceless photons that have journeyed from the farthest reaches of the cosmos. The mirror collects these faint rays of light, collimates them, and channels them toward a secondary mirror and onto the scientific instruments to produce an exceptionally sharp image. Webb's primary mirror boasts a diameter of 6.5 meters, making its light-collecting area vastly larger than Hubble's. It is constructed not as a single piece, but as a segmented array of 18 distinct hexagonal panels. This innovative design was a practical necessity, as a monolithic mirror of such a scale would be too large to fit inside the protective fairing of any available rocket. Consequently, these segments were engineered to fold compactly for launch and then unfurl, like a blossoming flower, once the telescope arrived at its operational orbit millions of kilometers from our planet. Each mirror segment is a hexagon, a 6-sided shape chosen to maximize the use of space and form a unified reflective surface with the fewest possible gaps. This configuration optically approximates an ideal circular mirror, which provides the best possible focus for concentrating collected light onto the detectors. For these segments, engineers selected beryllium, a light gray metal that is relatively lightweight, yet exceptionally hard and robust. A crucial advantage of this material is its unique capacity to hold its shape with nanometer-level precision, even in the extremely low temperatures of deep space. This structural stability is absolutely vital for the accurate collection of scientific data, as even the slightest warping of the mirror would result in distorted images. Having reviewed these technological achievements, we can turn to the most compelling question. What discoveries will the James Webb Space Telescope actually make? What cosmic secrets is it poised to uncover? Its cutting-edge technologies and advanced instruments, operating mainly in the infrared spectrum, will enable it to observe ancient, cold, and faint objects that Hubble,
despite its many successes, is simply unable to see.
The new observatory is engineered to pinpoint when and where the universe's first stars ignited, how the earliest quasars and supermassive black holes formed at the hearts of young galaxies, and the process by which these primordial galaxies began to merge into groups and superclusters. Perhaps the most fascinating and potentially transformative discovery Webb could offer involves the detailed analysis of exoplanets, worlds that orbit stars other than our Sun. The objective isn't merely to find them, but to identify planets similar to Earth that might even be habitable.
To be more specific, Webb's mission profile includes measuring the density of these planets, a key piece of data that will help scientists classify what they are observing: a gas giant, an ice world, or a rocky planet. This information is the first step in determining if such a world could potentially host life. With Webb, the scientific community expects to gather an unprecedented volume of data on the masses and diameters of distant worlds, which will in turn grant us new insights into the formation of our own solar system and galaxy.
The telescope's instrumentation will allow it to identify relatively cool exoplanets, including those with surface temperatures as low as 27 degrees Celsius, which is quite close to Earth's conditions. Webb will be capable of locating such objects at substantial distances, over 12 astronomical units from their parent stars, and as far as 15 light-years away from us. Furthermore, there are ambitious plans to investigate the atmospheres of these distant planets, which represents a massive leap in capability.
For context, the Spitzer and Hubble telescopes, throughout their many years of service, managed to analyze the atmospheric composition of roughly 100 exoplanets. According to the most conservative projections, the new telescope will be able to study the atmospheres of at least 300 exoplanets, and in much greater detail. Another primary target for the observatory will be the universe's oldest galaxies. While we now have a solid understanding of the structure and evolution of mature, nearby galaxies, our knowledge of those that formed in the cosmic dawn is still very limited.
Hubble can perceive the universe as it was approximately 400 million years after the Big Bang, while another great observatory, Planck, observed the cosmic microwave background radiation, the afterglow of creation from just 400,000 years after the universe began. Webb is specifically designed to bridge this enormous chronological divide, revealing what the very first stars and galaxies looked like during the first 3% of cosmic history. This new spacecraft promises not just to be a worthy successor to Hubble, but a revolutionary tool that will provide answers to fundamental questions that have remained unsolved until now. As I write these words, the telescope is closer than ever to finishing its long and intricate preparations for flight. It stands as a brilliant emblem of successful international partnership, causing people all over the world not only to await its completion with bated breath, but also to repeatedly ask the same question. When will the new telescope finally begin its long-awaited voyage into space? You might be experiencing a sense of déjà vu, as this project's history has been an almost unending sequence of delays since its conception in 1996. The telescope has faced nearly annual postponements and major budget increases, which have unfortunately been driven by the constant emergence of new technical problems within its highly sophisticated systems. Each of these issues required a mandatory and thorough resolution before launch could be considered, which pushed the new, and at that time final, launch date to March of 2021. If this long series of setbacks makes you feel frustrated, you might want to mentally picture a giant sad emoji to express your impatience. However, it is worth remembering that an entire fleet of space telescopes is already operating in various orbits around the Earth, the Sun, and at gravitationally stable Lagrange points. These observatories work together to cover the entire electromagnetic spectrum, from long radio waves to the highest energy gamma rays.
Perhaps a good place to begin our review of these other missions is with the Planck telescope, which was launched on May 14, 2009. The main objective for this European Space Observatory was the detailed study of the relic radiation, also known as the cosmic microwave background, which is the oldest light in the universe and is often described as a faint echo of the Big Bang. Thanks to the information acquired by Planck, scientists were able to create the most accurate and detailed map of this radiation, which has been preserved from the very earliest stages of the universe's existence. The minuscule temperature fluctuations on this map are in fact the seeds of all future cosmic structures, including galaxies and the vast clusters they form. During its mission, Planck accomplished a colossal amount of work, observing the first light in the cosmos, the first photons that could travel freely once the universe cooled down and became transparent.
On the subject of light, the Planck telescope's highly sensitive instruments enabled it to uncover a colossal cluster composed of thousands of galaxies, which functions as a gravitational lens. It also confirmed with exceptional precision that the spectrum of the universe's primordial density fluctuations contains a small but vital deviation from complete homogeneity. This finding is critically important to inflationary theory, the model that describes the very first instant of cosmic existence. Before the advent of the Webb telescope, the largest instrument in the infrared spectrum was Herschel, another European spacecraft featuring a 3.5-meter mirror. It performed its mission flawlessly until June 17, 2013, when it unfortunately ran out of its supply of more than 2 tons of liquid helium. This coolant was absolutely necessary to bring its infrared detectors down to their operational temperatures. Throughout its operational life, Herschel investigated the processes of how galaxies formed and evolved in the early universe. It also analyzed the chemical composition of atmospheres and surfaces on bodies within our solar system, such as planets, comets, and their moons. Its main objective, however, was to observe the formation of stars and their complex relationship with the surrounding interstellar medium, which resulted in many breathtakingly beautiful and scientifically valuable images of galactic gas and dust nebulae. For example, if you examine its images of the giant molecular cloud AB3, located 6,200 light-years from Earth, you can see yellow dots that represent protostars, the very embryos of low-mass stars. Nearby, you can also observe more massive embryonic stars, which are colored blue in the image to signify their much higher temperatures. Among the optical telescopes that function in visible light, the most massive, celebrated, and unquestionably deserving of praise is the Hubble Space Telescope. Its main mirror has a diameter of 2.4 meters, and it was sent into orbit on April 24, 1990. Following 5 extremely complex servicing missions conducted by astronauts in the vacuum of space, it continues its relentless work to this day. You should understand that the images Hubble produces are not what you would consider typical photographs. A vast quantity of information about celestial objects is invisible in the optical range. Many of these objects, including nebulae, or the active nuclei of galaxies, emit powerfully in other parts of the spectrum, like ultraviolet or infrared. Hubble is outfitted with numerous instruments and filters that allow it to collect this data, which astronomers on Earth later process and combine into a single, brilliantly colored image. The richness and intensity of these colors are created by the different emission ranges of the stars themselves, the particles of ionized gas, and the light that is reflected from clouds of dust. The quantity of images captured by the telescope is truly astonishing. For example, in one of its most iconic images, the Hubble Ultra Deep Field, which had a total exposure time of 2 million seconds, you can find approximately 5,500 galaxies. The farthest of those galaxies is 13.2 billion light-years away from us. In this historic photograph, the youngest captured galaxy was formed a mere 600 million years after the Big Bang. Then you have the famous pillars of creation, enormous columns of cold gas and dust, so named because new stars are born from these clusters deep within them, and also because their silhouettes suggest such majestic forms. The image itself shows only a tiny portion of the central area of the gigantic Eagle Nebula. And here you can see the rows of galaxies, an object known as ARP 273, which provides a stunning illustration of gravitational interaction, a sort of cosmic dance between galaxies that have moved too close to one another. The Sombrero Galaxy, with its distinctive dark ring of dust, is situated on the southern border of the Virgo constellation. It is so bright that you can observe it even with amateur home telescopes. In this image, Hubble captured the active star-forming region S106. Its veil of dust has characteristic gaps at the top and bottom, through which material from the central star escapes with particular force, creating a shape that might remind you of an hourglass, or a well-known optical illusion. And here you can see the cosmic butterfly, the incredibly beautiful planetary nebula NGC 6302, which is emerging from the remnants of a dying star. This is just a small fraction of the many incredible images available. Within the ultraviolet range of wavelengths, Hubble was and still is the largest telescope in operation. With its capabilities, unique research into non-stationary phenomena has been conducted, including powerful ejections and absorptions of matter, as well as stellar explosions. Understanding these events is key to figuring out how gas and dust nebulae are formed and evolve, making Hubble a truly unique and multifaceted observatory. Among X-ray observatories, the Chandra X-ray Observatory is particularly noteworthy. Its launch mass was nearly 23 tons, which set an absolute record for the heaviest payload ever deployed into orbit by the space shuttles. It was launched on July 23, 1999, aboard the shuttle Columbia. The telescope continues to operate successfully today, giving you a view into the hottest and most energetic corners of the universe. During its observations of the famous Crab Nebula, the remnants of a supernova that exploded almost 1,000 years ago, the Chandra Observatory was able to distinguish complex shock waves surrounding the central pulsar. These features had previously been missed by other telescopes. It also identified faint X-ray emissions from Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, and discovered a new type of black hole in the galaxy M82, which represents the missing evolutionary link between stellar mass black holes and the supermassive variety found in galactic cores. Next is the Fermi Telescope, a 4-ton observatory that was launched on June 11, 2008. A Delta II rocket delivered it into an orbit 550 kilometers high. This telescope works in the highest energy gamma-ray part of the electromagnetic spectrum. The first major discovery made by this observatory was the detection of a gamma-ray pulsar located within the supernova remnant known as CTE1. Since 2010, the Fermi telescope has detected some of the most intense gamma-ray bursts ever recorded, which originate from novae. These powerful eruptions happen in compact binary star systems, where material from one star is pulled onto its companion, triggering a massive thermonuclear explosion. Among the observatory's most breathtaking findings are colossal bubble-shaped structures, each spanning up to 50,000 light-years, positioned directly above and below the center of our galaxy. It is widely thought that these formations, now known as Fermi bubbles, are lingering evidence of past eruptions from the supermassive black hole at the heart of the Milky Way. Looking to the future, the Space Observatory set to follow the Webb will feature a primary mirror with a 10-meter diameter, with its launch anticipated sometime after the year 2025. Naturally, countless other fascinating and significant space missions and celestial structures exist. If you happen to be familiar with any of them, please share what you know in the comments, as it would be fascinating for everyone to learn about them. After 2 decades of dedicated work, an ambitious project reached its culmination as the intricate Space Observatory, folded up like a piece of giant origami, was successfully sent into orbit. This monumental occasion unfolded on December 25th, when an Ariane 5 rocket ascended from the Kourou spaceport in French Guiana, carrying the invaluable James Webb Space Telescope. The launch vehicle performed with absolute perfection, setting the massive telescope on its precise trajectory with the exact angle and acceleration required for its mission.
Having flawlessly detached from the rocket's final stage, the James Webb Telescope began its long, solitary voyage to its operational outpost, approximately 1.5 million kilometers from our planet. The journey was initiated with such remarkable accuracy that the observatory conserved a significant amount of its onboard fuel, which had been allocated for course corrections. As a result, experts now project that its operational lifespan could extend well beyond 10 years, far surpassing the mission's minimum guaranteed duration of just 5 years.
The final images captured by a camera on the rocket's upper stage offered a last live view of the telescope as it receded into the distance, on a path that would see it arrive at its destination by the end of that month. At that point, it had already traveled beyond the moon's orbit. Further evidence of the launch's success came from the astonishingly rapid deployment of its solar panel array, which unfolded just 70 seconds after the telescope separated from the rocket, rather than the several minutes originally scheduled. This early deployment was initiated by the telescope's onboard computers, which, after assessing all the relevant data, determined that the conditions were perfect for this critical maneuver and issued the command. Over the subsequent month, NASA specialists undertook the painstaking and high-stakes process of sequentially unfurling this astronomical Optimus Prime, a procedure that rivaled any transformer from a Hollywood film. Now, however, the telescope is completely assembled, including its immense 6.5-meter concave mirror, composed of 18 hexagonal segments made from lightweight beryllium and coated in a fine layer of gold for optimal performance.